Hi, welcome to section 4.3. In today's video, we will finally learn how to solve homogeneous linear differential equations. In the last video, we took a look at reduction of order. So if we have one solution, how do we find a second linearly independent solution? And then if you remember from the first video of this unit, we took a look at the difference between homogeneous and non-homogeneous linear differential equations. So if you remember, homogeneous ones are set equal to 0. We talked about to solve a non-homogeneous equation, you would have to solve the corresponding homogeneous one first. So that's what we're going to learn how to do, is how do we solve a homogeneous linear differential equation, and ultimately that will take us to non-homogeneous ones. Now, before we actually take a look at the solving part, there's a little bit of background that we need to talk about. First thing is, let's talk about complex numbers. So there's something that you may or may not have seen before, which is called the complex plane. The complex plane has a real axis and an imaginary axis. So if we wanted to plot this number a plus bi, we would go over a units, and then we would go up b units on the imaginary axis, and that would be our point. Now, drawing out to that point, we can also express that same point by the radius and the angle theta that it makes with the real axis. A few things to know is that r squared, hopefully you can tell, is going to be a squared at b squared. We know that a, if we think back to our unit circle, can be calculated finding r cosine of theta, and b can be calculated using r sine of theta. Any complex number then, z, which is equal to a plus bi, can be written as our a component is r cosine theta, and our b component is r sine of theta multiplied by I. If we factor out the r, that is cosine theta, add I times sine of theta, or an abbreviation for this is r cis theta. So this is an abbreviation for another way to express a complex number. And again, we're going to be using that eventually. Next thing that we need to talk about or review is some series. So if we take this first series, x to the n over n factorial, which looks like this if we expand it, that converges, if we remember, to e to the x. And then we have these next two series that you've also seen. We've expanded them for the first three terms. That second one, which has the 2 factorial, converges to cosine of x. And then the 2n plus 1, rather, converges to sine of x. Okay, so we're going to use some of those series. So what we're going to do is we are going to let x be equal to I theta, and we're going to use the series for e to the x. So what that gives us then is e to the I theta is equal to 1, add I theta, add I squared theta squared over 2 factorial, add I to the third, theta to the third over 3 factorial, add I to the fourth, theta to the fourth over 4 factorial, so on and so forth. Okay, so first thing I want us to notice, or next thing I want us to notice, this 1 is real, this I theta is imaginary, I squared, remember, is -1, so this term is real. That I to the fourth is just 1, so this term is real. Every other term then is imaginary. So if we rewrite this series in terms of the real parts and the imaginary parts, we're going to get 1, subtract theta squared over 2 factorial, add theta to the fourth over 4 factorial, so on and so forth. And then we have I multiplied by theta, subtract theta to the third over 3 factorial, add theta to the fifth over 5 factorial, so on and so forth. So again, this is our real portion and our imaginary portion. Well, both of those series should look familiar from above. This is cosine theta, add I sine of theta. Okay, so what that leads us to then is our e to the I theta is equal to cosine of theta, add I sine of theta. Can also be written as e to the I theta is equal to cis theta, using the abbreviation from above. This is called Euler's formula. That's Euler, not Euler. And we're going to use that in a little bit. Another way to express this, or something else we get from it, is that e to the pi I add 1 is equal to 0. So if we make our theta pi, we can get e to the pi I add 1 is equal to 0. Okay, so at this point, you should probably be thinking, why do I need to know all of this? Where is this going? So that's what we're going to talk about next, is how does this all apply to differential equations? Okay, so let's start with, we have this differential equation, dy dx, add a y equals 0. We know that this has solution y equals c1 e to the negative ax, right? And we can find that just by separation. But what happens if we have higher order equations? So we have a times y double prime, b y prime plus cy equals 0. So what happens now if we have this second order equation instead of a first one? Well, an educated guess, maybe y equals e to the mx is a solution. Now, how can we verify or check if this is in fact a solution? Well, of course, we can plug it back into our equation. So we'll have y equals e to the mx. Y prime then is going to be m e to the mx, and our second derivative will be m squared e to the mx. So then if we substitute those into our equation, we have a m squared e to the mx, add b m e to the mx, add c e to the mx, and we want to know, does that equal 0? Is this in fact a solution? Let's factor out e to the mx, which gives us am squared, add bm, add c. Again, we want to know if this equals 0. Now, we know that e to the mx cannot be 0, which means the only way that this y term is a solution is if this factor is equal to 0. So if y equals e to the mx is a solution, then m must be a root of that factor above, am squared, add bm, add c equals 0. So that's what we're going to be investigating now. We're going to be looking at this factor, which is called a characteristic equation, and we're going to be finding those solutions or those roots. So here we go. This next objective, we are using roots of the characteristic equation, which is that one above, to produce the complete solution of a linear homogeneous differential equation. So there are two terms, just so you know. It's called a characteristic equation, also could be called an auxiliary equation. So there are three different equations if we're going to solve this, or there are three different possibilities, three different cases if we're going to solve this quadratic above. The first case is that that quadratic has two real roots, or there's one real root that happens twice, so root 1 and root 2 are the same. Or last case, there are two complex roots. So each of these three cases are going to look different in terms of producing this complete solution, and so we're going to look at all three cases separately. Case number 1 is that our auxiliary equation has two real roots, and we're going to call those roots m1 and m2. So what that means then is that our first solution is e to the m1x, and our second solution is e to the m2x. So our goal is to form the complete solution, or the general solution. So remember, for a general solution, because this is second order, we are going to need two linearly independent solutions. So the question is, how do we determine if these two solutions are linearly independent? Well, one way that we can do that is we can look at the Wronskian. So that's what we're going to do. Remember, determinant of a matrix, we have the first solution, and then the derivative of that one, second solution, derivative of that one. And so we're calculating this determinant. So we get m2e to the m1x plus m2x, subtract m1e to the m1x, add m2x. So then simplifying that Wronskian, if I factor out e to the m1x, add m2x, I'm going to end up with m2 subtract m1. And so we want to know, does this Wronskian ever equal 0? Well, we know that this term is not 0. And we also know that m2 is different from m1, so that difference then is not 0. Okay, so what does that tell us then? What that leads us to is that y1 and y2 are linearly independent. Therefore, they form a fundamental set. And therefore, where this is leading us to is that the general solution, y, is going to be a linear combination of the two solutions. So it'll be c1e to the m1x, add c2e to the m2x, and this, of course, is by superposition. This formula is really important, so if I were you, I would make sure it was highlighted, bolded, starred, something like this. So this is the general solution, like we said, case number 1, when there are two real roots. Now let's take a look at the next case where we have one root that happens twice. Okay, so case number 2 is that we have one root that is equal to the second root. So we know then one solution is e to the mx. Because our equation is second order, we need two linearly independent solutions. We only have one though. So the question is, how do we find a second solution if we know the first? Well, of course, hopefully in your mind, you're thinking reduction of order. Woo! What we did the last set of notes. So if we remember from reduction of order, our second solution is going to be the first solution times the integral of e to the negative integral of p of x dx over y1 squared dx. Now, we need to remember, though, that this formula is when our ordinary differential equation has a lead coefficient of 1, which is not what we are looking at now. What we are looking at now is an ordinary differential equation where we have a times y double prime, add b y prime, add c times y equals 0, right? Does not have a lead coefficient of 1, so we're going to need to make it have a lead coefficient of 1. So we end up with y double prime, add b over a y prime, add c over a times y is equal to 0. Okay, so then in our second equation, that p of x is this term right there. So let's substitute that in and see if we can get a y2 that looks a little bit nicer or a little bit kinder. So we get e to the mx, and then we have the integral of e to the negative integral of b over a dx all over e to the 2mx dx. Okay, so thinking a little bit ahead, I don't love this b over a, right? I have m and x as terms, I have m and x as variables. I don't love the b over a, so is there a way that I can get rid of that? Well, if we have one root, we know that that root happens at the vertex, so we know that our m has to be negative b over 2a. So if we're thinking of a quadratic, and we know that that quadratic has only one root, that root has to happen at the vertex. So what that gives us then is that 2m is equal to negative b over a. Well, if I have negative b over a, that's 2m. So I can substitute that back in. So I get e to the mx times the integral of e to the integral of 2m dx over e to the 2mx dx. Well, this is just e to the mx times the integral of e to the 2mx over e to the 2mx dx. I ran out of room, so I'm going to continue over here, which is e to the mx times the integral of dx. So our second solution then is x e to the mx. So we have our second solution here. We have our first solution here, which therefore means that our general solution is y equals c1 e to the mx, add c2x e to the mx. And again, like we did with the last case, I would suggest you bold this, highlight it, put a star by it, but this is our general solution when our two roots end up being the same. Okay, and lastly, the last case when you are solving a quadratic equation is that you end up with two complex roots. And of course, if they're complex, they have to be conjugates. And just remember, this will happen when your discriminant of your equation is negative. I don't think I spelled that right. Okay, so in this case, we're going to let our first root be alpha add I times beta, which means our second root is alpha subtract I times beta, because we know that they're complex and they're conjugates. So then, because we have two roots and they're different, from case 1, we can write our general solution as c1 e to the alpha add I times beta x, add c2 e to the alpha subtract I times beta x. But hopefully we can tell this is not practical to us. This is not useful. We don't want imaginary parts or this alpha plus beta in our solutions. We want real functions. Okay, so if we want real functions, then the question is, where do we go from this? And this is where we're going to go back to that background in the beginning of the video. So we're going to use this idea that e to the I theta is equal to cosine of theta, add I sine of theta. And remember, this is Euler's formula. So then, if we're looking at our imaginary parts up here, we have e to the I beta x. So we can write that then as cosine of beta x, add I times sine of beta x. Likewise, on that second term, we have e to the negative I beta x. So that can be written as cosine of beta x, subtract I sine of beta x. Okay, so what we're going to do is we're going to add those two, and we're going to subtract those two equations. And what those give us then is that e to the I beta x, add e to the negative I beta x, is just equal to 2 cosine of beta x. And e to the I beta x subtract e to the negative I beta x gives us 2I sine of beta x. Okay, so what we're going to do is we are going to keep these and use them in a little bit. And what we're going to do is we are actually going to return back to this equation up here. So from that equation above, we are going to let C1 equal C2 be 1 for our solution y1. And then we're going to let C1 equal 1 and C2 equal negative 1 for our second solution. Okay, so where that leaves us with then, or where that takes us next, is that y1 then is e to the alpha add I times beta x, add e to the alpha subtract I beta x, and y2 is e to the alpha add I beta x, subtract e to the alpha subtract I beta times x. Okay, so we're going to rewrite these then. If we take this y1 and we factor out e to the alpha x, we're going to end up with e to the I beta x, add e to the negative I beta x, which is what we saw here. So that y1 is really e to the alpha x multiplied by 2 cosine of beta x. So y1, our first solution, we're going to write as 2e to the alpha x cosine of beta x. Now remember, we've talked about we don't care about the constant. Okay, so likewise, same idea. We're going to do the same thing with y2. With y2, we're going to factor out e to the alpha x, and we're left with e to the I beta x, subtract e to the negative I beta x. So substituting back from above and simplifying, we get our y2 to be 2i e to the alpha x sine of beta x. Again, though, don't care about the constant. So finally, after all of this work, we have our two solutions. So now we can write our general solution. So we have our two linearly independent. So our general solution then becomes y equals, using these two, c1 e to the alpha x cosine of beta x, add c2 e to the alpha x sine of beta x. Also written as e to the alpha x times c1 cosine of beta x, add c2 sine of beta x. Okay, so this is our third and final general solution. So that was all of the derivation. You're not going to do that every single time you solve one of these homogeneous linear differential equations. Let's take a look at the first example and we'll talk about expectations. Okay, so first example, solve the initial value problem that is given. So first thing that you're going to notice is this is homogeneous, which is good. So what we're going to be doing is we're going to be solving the auxiliary equation. So that's the equation that comes from these constants. So we get m squared, subtract 4m, add 13 is equal to 0. So what we want to know then is what are our roots. So let's solve this auxiliary equation and then we can go from there. This quadratic does not factor, so I'm just going to jump right into quadratic formula. So I get 4 plus or minus the square root of 4 squared, subtract 4 times 1 times 13, all over 2. So underneath the square root, I end up with negative 36. So my roots then are 2 plus or minus 3i. Okay, so what we're going to do then is we're looking back at that case 3 at our general solution. So 2 is our alpha and 3 is our beta. And if you just go back and look at the solution, we get our general solution then to be y equals e to the alpha x. And then we have c1 cosine of beta x, add c2 sine of beta x. So that's it. That's the general solution. Now, ours is an initial value problem, so we're going to have to solve for c1 and c2 using these two conditions. So starting with y0 is equal to negative 1. We get negative 1 is equal to e to the 0, c1 times 1, add c2 times 0. So that gives me then that c1 is equal to negative 1. So now our equation is y equals e to the 2x times negative cosine of 3x, add c2 sine of 3x. And now we're going to go to that second condition. We get y0 is equal to 2, which means we're going to have to take the derivative. So our y prime then ends up being 2e to the 2x, negative cosine of 3x, add c2 sine of 3x, add e to the 2x multiplied by 3 sine of 3x, add 3c2 cosine of 3x. Sorry, obviously did not give myself enough room for that one. So now substituting in, we get 2 is equal to 2 times negative 1, add 1 times 0, add 3c2. And so if you trust me, you get C2 to be 4 over 3. So finally, where that leads us to then is our solution is y is equal to e to the 2x times negative cosine of 3x, add 4/3 sine of 3x. Okay, so again, what your general process is. First thing, you're making sure that you have a homogeneous equation. Then what you're doing is you're writing your auxiliary equation that just comes from the coefficients, which will give you your roots. Those roots will then determine the form of your general solution. So in our case, our two roots were complex, so that was case number 3. We might end up with two roots that are the same, or we end up with two distinct real roots, and then you follow whatever the form is for the general solution. Now that we've seen this first example, let's talk about what happens if we have higher order differential equations. So the examples we looked at were all second order. What happens if we have third order or fourth order linear homogeneous differential equations? How do we solve those? So let's take a look at this section. To solve an nth order homogeneous linear differential equation of this form, so again, it's nth order, it's homogeneous, so it's set equal to 0, we have to solve the auxiliary equation. The auxiliary equation in this case will be that an, m to the nth power, a to the n minus 1, m to the n minus 1, all the way down to a1, and all of those a's are just constants, m to the first plus a of 0 equals 0. So we're still solving the auxiliary equation. The first case is that all of our roots are real, and they're distinct. So we have m roots, they're all real, and they're all different. So then the general solution would be of a similar form. We would get y is equal to c1 e to the m1x, add c2 e to the m2x, all the way to cn e to the mnx. So similar to what we saw in the previous case 1, except instead of only 2 terms, we're going to have all n terms. And then cases 2 and 3 we put together. So let's say that we have a root m1 that has multiplicity k. Then the solutions would be the following. So we would have e to the m1x. The next solution then would be x e to the m1x, like we saw before. And then we would have x squared e to the m1x, all the way up to x to the k minus 1 e to the m1x. So then our general solution must contain the linear combination of those solutions above. So it would have c1 e to the m1x, add c2x e to the m1x, add c3 x squared e to the m1x, all the way up to ck x to the k minus 1 e to the m1x. And that case 3, the distinct complex roots, is going to be the same as the case 3 from before. So to end this video, we're going to take a look at one more example, this time of a third order homogeneous linear differential equation. Okay, so here we go. We're solving this equation. And so notice it's homogeneous, which is great, so we know how to solve this. Our corresponding auxiliary or characteristic equation is going to be 3m to the third, add 5m squared, add 10m, subtract 4 is equal to 0. And so we need to find the roots of this equation. Now, we're going to need to factor this. We're doing this without a calculator, and so this might be a review for you. Maybe you've seen this before, maybe not, but we're going to need to factor. So what we're going to do is we're going to consider the possible roots. And so you might remember this maybe from Algebra 2, maybe you never saw it, but the possible roots are all the values of p divided by all the values of q. P are the factors of this last number, this last constant. Q are the factors of that first number. So P, the factors of 4, would be plus or minus 1, plus or minus 2, plus or minus 4. Q are the factors of 3, so plus or minus 1 and plus or minus 3. So then our possible rational roots, so that's really the case, our possible rational roots are P divided by Q. So that gives us plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. So all of those are possibilities. Now, how do we figure out which one is the correct root? Well, we're going to have to do some synthetic division to try it out. I always start with 1 or -1. So I'm going to start with 1. I'm going to use my coefficients. So I have 3, 5, 10, and -4. So if you remember, first number comes down. We then multiply and add down. Because we did not get a 0 there, that tells us that 1 is not a root. And you would keep going. Now, practically, when you're doing this in class or on your homework, don't waste time doing synthetic division a bunch of times. Just use your calculator. I will tell you that 1/3 ends up being a root. So we're going to take 3, 5, 10, and -4, do our synthetic division. As you see, we got 0, which means that 1/3 is a root. So when we factor then that auxiliary equation, we end up with m subtract 1/3, and then the other factor comes from here, which is 3m squared, add 6m, add 12 is equal to 0. Okay, so then this factor, we can try to factor again. I'll tell you it doesn't factor, so you're going to use the quadratic formula. So what we get then is we get a root of 1/3, and then our other roots are -1 plus or minus root 3i. So our general solution then is going to be the linear combination of all three of these roots. So we get y is equal to c1 e to the 1/3 x. And then we have an alpha of -1 and a beta of root 3. So we get plus e to the -x times c2 cosine of root 3x, add c3 sine of root 3x. And that is our solution. Okay, so at this point we now know how to solve homogeneous linear differential equations. So you're going to look at your auxiliary equation and find the roots and go from there. Ultimately, as I said earlier in the video, we're going to add on to this moving forward by solving non-homogeneous differential equations. But you're always going to have to come back to the homogeneous version first. Now, one quick reminder for something that you're going to see on your homework is how do you factor something of the form a cubed plus or minus b cubed. So for example, 27x cubed subtract 1. So I will tell you what I do. For a cubed plus or minus b cubed, first set of parentheses is just going to be an a and a b, and then we have a squared, then we multiply them, and then we have a squared. To remember the signs, it's same, opposite, always positive. So, for example, if we want to factor this 27x cubed subtract 1, so this is 3x cubed subtract 1 cubed. So I would have a 3x and a 1. This will be a 9x squared, a 3x, and a 1. So again, same sign, opposite sign, always positive. So if we had a negative, this will be a negative, positive, always positive. And I will just tell you this second factor in a sum of or difference of cubes is never going to factor again. So you wouldn't be able to factor that one if you were solving this. So if it were set equal to 0, you'd have to do a quadratic formula. Okay, so there you go. Now you know how to solve homogeneous linear differential equations. Until next time, thanks for watching.